Welcome to lecture 18. In this lecture, we will introduce another heap called Fibonacci heap. So this heap also supports the union operation as in the case for the binomial heap. However, Fibonacci heap has something that is very nice. Many of its operations has amortized cost of constant time. So they include the find mean, the insert, the union, and also the decrease key. And for the other operations, it will still have good amortized cost of order of log n. So extract mean and delete will have amortized cost of log n. So it means that if we run the algorithm using binomial heap and the Fibonacci heap, then the total time of the Fibonacci heap will not be worse than the total time of using a binomial heap, because for binomial heap, the time is order log n for each operations, and here it is amortized order of log n for every operation. So order 1 is still order of log n. So Fibonacci heap will not do worse in the case when we measure the total time. But however, because we are measuring things in the amortized case, it means that for a certain single extract mean operation, it can be really bad. Okay, so it says that for many extract mean together, if we consider them in total, it will be okay. But a certain single extract mean suddenly could have a worst case cost something like up to order of log n, order of n. And similarly, for decrease key, it says order of 1 amortized time. So it doesn't mean that worst case it is still order 1. Worst case for decrease key, it could be up to order of n as well. So it depends on situation. Sometimes we want to use a Fibonacci heap, sometimes we want to use a binomial heap. This lecture will talk about the operations of this Fibonacci heap. And in the next lecture, we will analyze the corresponding amortized cost. Okay, so Fibonacci heap is something that is similar to a binomial heap in the sense that it consists of a set of component trees to allow flexibility. And for the component trees, the nodes inside each component tree, they will follow the heap property as well, so that the value of a node is always larger than the value of its parent. But unlike binomial heap, Fibonacci heap has something that is very uncontrollable. So first of all, there is no limit on the number of trees that it can have. So for binomial heap, there will be only order of log n trees, but for Fibonacci heap, the number of trees could be up to n. So in that case, extract mean, in the worst case, it may take up to an order of n time. And another bad thing about a Fibonacci heap is that for the component tree, the height is also not bounded. So when the height is not bounded, then we will have a tree such that it is very, very, very tall. So when we perform decrease key, we need to use another method. So previously in the binomial heap or in the binary heap, we just need to swap the decrease node with the parent until the heap property is preserved. But here, for the Fibonacci heap, we do this in a different way so that decrease key can be done faster. So this is the bad thing about Fibonacci heap that makes us to have some new measures to make it work efficiently. Okay, so let us briefly talk about the find mean, insert, and union operation first. Okay. So first of all, the heap will always maintain the pointer to the current minimum value node. Let's call it the min h pointer for the heap h. So in that case, with this pointer, find mean can be done in order 1 time. So we just follow the pointer and see the value of the node. Now, how do we do union? Okay, when we have two Fibonacci heaps, h1 and h2, we just need to place the two heaps together as if it is a single heap and update the minimum pointer. So previously, you have the minimum pointer for h1 and the minimum pointer for h2, and we just find out which one has a smaller value, and then we update the minimum pointer for this new heap, the combined heap, to be the one that is pointing at the smaller value. And insert, as if the case for binomial heap, it is a special case of union. And we can see that all these operations take constant time. Yeah, find min just follow the minimum pointer. Union just need to update the minimum pointer, and insert is a special case of union. So everything is done in order one time. So let's see this example. Suppose that before union, this is what happens. So heap 1 is a Fibonacci heap, and then you will see that, oh, there are many trees together. So 1 tree, 2 tree, 3 trees, 4 trees. So it has 4 component trees. And then this is another Fibonacci heap H2, it has 2 component trees. Now when we perform union, what do? We just remove this boundary, place them together, and then update the minimum pointer. So previously, this is the minimum of H1, this is the minimum of H2. After that, we compare which one is smaller, and then set the minimum to be the minimum of these two. So done. So the union operation takes constant time. And now we will talk about the bound on the maximum degree in the next lecture. But here, let us state what we know. Okay. So for Fibonacci heap, there is no bound on the number of trees. There is no bound on the height. But however, there will be a bound on the maximum degree of any node. Now to help Fibonacci heap to do this, okay, we will apply a certain called marking policy, a special marking policy, so that the degree of the node is controlled. The idea of this marking policy is to ensure that if a node has a large degree, then it must have many nodes as its descendants. So in that case, it is difficult for a node to have many descendants, so it is difficult for a node to have a large degree. So this is the basic idea. So in the next lecture, we will show that the degree of any node within this Fibonacci heap will be smaller than or equal to this number, a constant 1.4405 multiplied by log n. So the maximum degree of a node is order of log n. Okay, now, how do we perform extract min? Okay, actually, extract min has 2 key steps, or we list 3 here, but actually 2 of them are the main key steps. Okay, the 2 key steps are the first step and the second step, because the last step is just updating the minimum pointer. Okay, now the first step here is that because extract min will need to remove the node with the minimum value, so the first step is to remove this node. Now when we remove a node, and this node must be a certain root of some component tree, so in that case, the children of this removed node will now form the roots of the new subtrees. Okay, so all the children of this removed node will become the roots of a tree. So we will have a bunch of new trees formed. And the next part here is consolidate. This consolidated step allows us to have a chance to make the Fibonacci heap more structured. Now remember that we will need, after this removal of this root node, the current minimum is gone. So we will need to find out the minimum of the remaining nodes. Okay. Now to do so, we have to visit the roots of every remaining trees. So why don't we do something more so that we make the overall structure more nice? Okay, so in that case, we will perform this consolidate operation so that we will join the roots of the tree nodes if they have the same degree. So just like the case for the binomial heap. So when we see 2 roots with the same degree, we join them together. So in the end, after this operation, all the roots will have distinct degrees. Now 1 and 2 are the key steps, and after that, we will maintain the minimum pointer as well. So we will have the update operation of the minimum pointer. So let's see an example. Okay, so at the beginning, let's say this is the heap that we have. It has a bunch of trees, and this is the minimum value. So the first step is to remove this one. So when we remove this, it's gone, and then the children becomes the root of trees. Okay, so we now have more trees now. And what we do? Okay, we will look at trees one by one in any order. And if we see that, okay, let's say we look at these two, they have the same degree, we join them together. We join one root with the other root. Okay, the smaller of the roots becomes the new root. So we join them. And then let's say we see these two are of same degree. So we join them together, join. And now we see that these two have the same degree. This root has degree 1, this root has degree 1. So we join them, Okay, when we join them, we can join them in any way. Okay, so it can be placed as the leftmost child or rightmost child or any child. So let's place it here. And at this moment, after all this operation, all the roots of the trees that we see are having distinct degrees. So we are done. So this is the end of the consolidated step, and then we will update the minimum pointer. Okay. So this is how extract min is done. Now let us revisit this again. So these are some key points. So first of all, the consolidation step will examine each tree one by one and in arbitrary order. Okay, so in any order. But to facilitate this process, we will construct an array A of size 1.m, where m is the maximum degree of all nodes. So this is like 1.4405 times log n. So you can set it to be some order log n number here, such that A of k will store a tree whose root is degree k. Then in any case, when we process a tree, we look at the degree of the node, and then we will store it in this array A. But when we see two trees with the same root degree, then we will link them together. So when we see two trees, let's say we have already a tree stored at A2, it has degree 2. And now we have another tree of degree 2. So we now see that there are two trees of degree 2 for its root, and then we join them together to make it into a degree 3 tree. So we will store it at A3. But if at that time A3 has also another tree, then we will continue to do this step so that we join the two roots together to get a tree with degree 4 and so on and so forth. So in that case, this AK will keep track of at most one tree of a specific degree at any time. This allows us to do this operation efficiently. Okay, so that's for extract min. Now let us talk about decrease key. So how decrease key is done. Okay, as mentioned before, binary heap or binomial heap, the decrease key operation is done by swapping the node that has decreased with the parent repeatedly. But for Fibonacci heap, we cannot do so because the tree height is unbounded. So what do we do? Okay, we are using a completely different approach. So the idea is super simple, okay, because eventually we want decrease key to have amortized cost of constant time. So you can imagine that most of the operation of decrease key takes constant time. Yeah, otherwise, how can the average to be constant? Okay. Now when we perform decrease key of a certain node x, let's say we are going to decrease of this node 21. Let's change the value into value 3. So we just go ahead and decrease the value to the target value. So let's change it to 3. But when it is changed to 3, we will find that the heap property is not preserved here because it is a smaller value. The parent is now having a larger value, so it's not right. So in that case, we simply detach the node from its parent, making this a new root. So in that case, 21 first becomes a 3, and then 3, and this edge is now removed. So 3 becomes another node, and after that we update the minimum pointer. So the minimum pointer, if needed, we will update it. So in that case, this node simply loses this child. Okay. So if there is nothing wrong, for instance, suppose the decreased key here is not to 3, but let's change it to 20 instead. If there is nothing wrong, then we just update the value. But if it is going to be a smaller value than the parent, we detach the node from the parent. Okay? But then we cannot do this freely. Okay? So if we do not have any measures on this this detachment, so for instance, let's look at this tree. Okay, if we decrease key, we detach this node. Decrease key, we detach this from the parent. Decrease, detach. We may usually, or we may eventually, could get a node such that it has many children. So we will have a case that a node with large degree, it has very large degree, but then the total number of descendants is not a lot. It is just equal to the number of degrees, so it's not enough for us. We actually need, for a large degree node, we will need to have exponential number of descendants. So this is not acceptable for this Fibonacci heap. So this is not good. So that because of this, we will need some other measure. Okay. So we will now have a concept of marking. As you may observe, nodes in this heap, some of them you will have a special color of it. So we call them the mark node. So we will talk about what is meant by marking. Okay. So first of all, if a node V loses a child for the first time, then we will mark the node. So for instance, this is the case. So let's say this is 21, we change it to 3. So after we change it to a smaller value, then we have this edge removed. So the node 19 will have now lost one of the children. So when it loses a child, it becomes a marked node. Is that okay? But on the other hand, if a node loses a child for the second time, then this node may now contain very few descendants. So in that case, what we do here is that we will detach the node from its parent and unmark V. So because we don't want a node with few descendants to be kept in the heap, in the component tree there. So we will see an example. So basically, this detachment avoids the parent of V from linking to a subtree with very few descendants. So let's see an example. So for instance, when we decrease key to 18, this node will now have a smaller value. But then it is still okay. 18 is still smaller than 15, so we don't need to do anything. And next, when we perform decrease key of this to 3, then this changes to 3, and then we have this detachment. So we have this cut. We are cutting this edge. When we cut the edge, we will mark the parent. And now let's change the value of this one. Now when we change the value of this one to 14, we will cut this edge. So 35 becomes 14 and becomes a single root. And now, but then this parent has already lost a child. So this has lost a child. And now it is losing the second child. So what does that mean? So it means that we are going to perform this cut, because when the node loses the second child, we will cut it, detach it from the parent, and also unmark it. So we will detach it and unmark it. And now this goes to this 19. This 19 now loses another child. It has lost a child before. So in that case, we will cut this edge. Yeah, we will cut this edge and remove this from parent. And then it's like this. And then this node 15, it has now lost a child. So using our rule, we should have marked it. But here, Actually, we do not need to mark it. It is because it is already the root node of the tree. So remember, the marking policy is to avoid the parent of a node from linking to too many nodes with few descendants. So here, this node is already a root. It doesn't have another parent for this one. So whether it is marked or not, it doesn't matter. Okay, so this is an example run of this decrease key. So there are the remarks. So first of all, the tree root, okay, the tree root, because it doesn't have any parent, so the tree root, we don't need to keep track of how many child it has lost. So the tree roots can always be unmarked if you want to. So this is an optional operation. And also we have also seen this one. So when a certain node X is detached from its parent, this may continuously or further create an event of the parent detaching from its parent. So for instance, when this node is changed to a smaller value, it creates a cut. Then it creates the scenario that the parent of this one, this node 27, also creates a cut. And then after that, it creates the scenario that this 19 also creates this cut. Is that okay? So in that case, there could be a series of cutting that is involved. And this series of cutting, we call it cascading cuts. So it's like one triggering another cut and another cut triggering another cut and so on and so forth. And because the height of a component tree can be up to order of n, in that case, the cascading cut event could have length like order of n. So it means that the worst case running time for decrease key could be up to order of n. And finally, in the next lecture, so what remains to do, okay, we will show that the marking policy is useful so that it allows us to control the degree of a node. The degree of a node is important because for the extract min operation, because we will need to create an array such that this array is for consolidation. We don't want the array to be very, very long. We want the array to be of size of order of log n. Okay, so in that case, we will show that the marking policy is useful, and then we will also analyze the amortized cost of each operation. So that's all for the operations part of this Fibonacci heap. Thank you.